Oh yeah. Homeworks. Turn them in over there in the four piles as usual by last name. Okay. So today we are going to do chapter 9. Okay. Um, and then next week will kind of be this catch-all week where I'm going to try to make sure we fully understand this hypothesis testing stuff. And there's a couple topics from chapter 12, but it's very light, okay, in terms of new stuff, okay? And then the week after next, we'll have a review. It'll be a review day. And then the week after that is the final exam, and that's it for the course. And that will be it for our seeing each other. So there is a quiz next week, okay? So today we are going to do hypothesis testing for numeric variables. Last week was all hypothesis testing for categorical variables. And this week is hypothesis testing for numeric variables where we're dealing with means. And after this week, pretty much almost everything you need to know for the final exam, you'll know. There's a couple more things that we'll learn next week, but it's pretty light, just a few topics that should be relatively easy, and I'm just going to really spend a lot of time going over stuff. And so on the website, there's already a practice final exam posted. Okay, the practice final is, I think, is a very good tool that will help you be prepared for the final exam. And so I definitely recommend that you check that out, and we'll go from there. Yes, Eric.
Is there a lot from chapter 8 on the final?
Yeah. There's quite a bit from chapter 8, and today we're doing chapter 9. There's quite a bit. Okay. So how did the homework for chapter 8 go?
Pretty good.
Hard, right? It's a tough chapter, but I hope I presented the material in a way that you can kind of go through the process and answer the problems. Okay. But yeah, the final exam will be very heavy on chapters 8 and 9. Because I feel like the whole course has been building up to these final chapters. Okay, where you learned all about the normal distribution and all of this data. So that's a big part of statistics is this statistical inference. So chapters 8 and 9 will be pretty heavy here. Okay. So yeah, again, chapter 8 we did hypothesis testing, and it was all for categorical variables. Okay, so it was, what proportion of people were able to recover or quit smoking, right? Proportion of users using the nicotine gum versus placebo. What proportion were able to quit smoking? So whether someone is able to quit smoking or was unable to quit smoking, that's a categorical variable. They either quit or they didn't quit. Okay, it's not a numeric variable, it's categorical, but we turn it into a proportion. So you see numbers and you're dealing with numbers, but it's for a categorical variable of quit smoking or didn't quit smoking. Okay. Today we are going to deal with numeric variables, and so what's a numeric variable? Numbers. Okay, thank you. Okay, so let's let me write this. Okay, so we're going to do hypothesis testing and confidence intervals. For numeric variables. Alright, so just recap. Categorical variables tell us what? Categories, thank you. It tells us what kind or what type, right? And how do we summarize categorical variables? What kind of charts do we use? Charts and graphs. Not a histogram. A bar chart. Okay, a bar chart's one. And what kind of tables? Frequency tables. Thank you, thank you. I thought I was going to go home and cry tonight. So categorical variables, we use bar charts and frequency tables. And for numeric variables, what do we use? Histograms, box plots. Well, for one numeric variable, we don't use scatter plots. Scatter plots are for two numeric variables. Dot plots, okay. And then, and how do we summarize numeric variables? We describe the center. What else? Spread. Shape. Okay, okay. Good, good. All right. So we haven't forgotten everything that we learned 6 weeks ago. What do we use to describe the center?
Mean.
The mean. Great. Mean or median. Okay. So we'll say we'll talk about the center, and we use the mean or the median. Okay, but in this case we're going to use the mean. And then for spread, what are numbers we can use? Standard deviation. Great. Standard deviation, okay, also range and IQR. Okay, hypothesis testing and confidence intervals for numeric variables, okay. And then we've got the center, we use the mean, and the spread, we use the standard deviation here, okay. What was the idea when we created a confidence interval when we were dealing with a categorical variable?
How
Yeah.
accurate?
How confident we are about the population proportion?
We would create how confident we are about the population proportion, and we would say I'm 95% confident that the population proportion is between 30% and 40% or something like that, right? So I'm 90% confident that the proportion of, people in the population that I don't know, own a car, I don't know, is between this percentage and that percentage, okay. And the idea was we gathered a sample, and our confidence interval is based on just the data that we saw in the sample, right? We have no idea what the population looks like, but based on what we see in a sample, we can say something about the population. This is the whole idea of inference, right? Inference with a confidence interval, we observe a sample. Okay. And based on the sample, we make a statement, make a confidence statement about the population. And so in chapter 7, we observe a sample, and we find from the sample, what do we find? A sample proportion, okay? And what symbol do we use for our sample proportion? P-hat, good, okay? And based on this sample, we make a confidence interval about, and the confidence interval is about what? It's not about p-hat, but it's about p, the proportion in the population, okay? So, make a confidence interval, or CI, for p, population proportion. Okay, and we would say something like the confidence interval ends up being is p hat plus or minus what?
Margin error.
The margin of error, which is z star times our standard error, right? And we would say I'm 90 whatever % confident that p is in between the ends of my confidence interval. This is feeling good for everyone?
Yeah.
At least familiar, I hope. Okay, so today, with chapter 9, okay, similar process. We observe a sample. This time it's for a numeric variable. So instead of finding p hat, what do you think we're going to find? No. P hat is the sample proportion. So when we're dealing with a numeric variable, we can't find a sample proportion, right? What can we find instead? The sample mean. Find the sample mean, and what symbol is the sample mean? X bar. Thank you. Thank you. All right. I hope we're all okay here. Okay. And so based on this sample where we found X bar, we're going to make a confidence interval for what? So when we dealt with proportions, we found the sample proportion p hat, and we made a confidence interval for the population proportion p. So for a sample, for a numeric variable, we find a sample and we find the sample mean, x bar, and we're going to make a statement about the what? Mean of the population. Is that what you said? Okay, I'm sorry, I didn't hear you. Okay, make a statement, make a confidence interval for the mean of the population, which is, what symbol do we use there?
Mu.
Mu. Okay, make a confidence interval for mu, which is the population mean. Okay. So today we're going to see a lot of symbols and a lot of like formulas and equations, but the concept is parallel to what we've already learned. Okay, so we learned this in chapter 7 where we observe p hat and we make a confidence interval for p. This chapter we observe x bar and we're making a confidence interval for mu. Okay. And our confidence interval here, okay, what do you think goes in the middle? X bar goes in the middle. And then I'll put the rest, it's going to be plus or minus. This time we're going to use t star rather than z star times our standard error. Okay? So it's very similar in format, and the concept is the same. It's just now we're using a numeric variable. Okay? Well, I'll explain t in a moment here. Okay? I don't fully remember what exactly happened in the book, but I know when we only learned how to make confidence intervals for categorical variables in chapter 7 so far. Okay, so if I could, I'm going to pass out some tables here. This is probably too many, but just take one and pass the rest down, and I hope everybody gets one. We'll look at that in a moment, or in a little bit. Okay. So again, overall, the idea for a confidence interval is we observe a sample. Based on the sample, we're making a statement about the population. And here, for numeric variables, okay, so for a numeric variable, we observe a sample. Okay, and we find the sample mean x bar.
Oh, sorry. Thank you.
This is our estimate of mu, the population mean. Okay. In our sample, we also find the sample standard deviation. Standard deviation, S. Okay. And we will use that to create our standard error. Okay, so everybody got one of these tables? You got some extras there? Okay, so hang on to these tables. You'll need one. You'll need to bring it for the quiz next week. Okay. All right. So this gives us the list of values that we'll need to figure out what our t star is. Okay. Okay. So in the center of the interval. Okay. So again, in the confidence interval, we're going to put this is a confidence interval for mu, okay, which means it's based on one sample. And that's what it is. X bar plus or minus t star times our standard error, okay, and the standard error is equal to the standard deviation S divided by the square root of n, the square root of our sample size. Okay. So let's try out a new thing. Alright, so just name something that we might be interested in. Pizza. Okay. And what about pizza? A numeric variable that we could look up about pizza. Okay. How many pieces of pepperoni are on a pepperoni pizza? Okay. So let's try to define this a little bit better. Okay. So we say, you know, what is the average number of pepperoni pieces on a pizza, okay? And so to be specific, let's say size large, Costco only makes one size pizza. Huh? Oh man, Costco pizza is the best.
It is.
Slice of pizza for $2 or an entire giant thing for $10. And you don't even need a membership card. I live pretty close to a Costco. If I'm not feeling, well, I don't need to tell you about my Costco pizza eating habits. So anyway, it's good stuff. All right. All right. So anyway, and they're very generous with their pepperoni. Okay. So if you like grease, it's excellent. Okay. So anyway, so we go there, and just to make sure we're getting a random sample, we go around the nation to all the different Costco places and order a large pizza and count how many pieces of pepperoni. Okay, so let's say we go and we say, okay, so we keep track of the number of pepperoni pieces. All right, so let's say we go and then and we count one, and there's 49 pieces of pepperoni on a pizza. I don't know. I'm just making up numbers here. Okay, and then and on another one there's 55, and on another one there's probably even more than this. Okay, we'll say 60 and 57 and 53. Okay. So here I've looked at 5 pizzas from Costco, and I counted up the number of pepperoni pieces on their slices of pizza. Okay, or on their pizzas. So so we say, what is the average number of pepperoni pieces? Okay. So our sample, X bar from the sample is I add these up and I divide by 5, right? Okay, so we figure that out. 54.8. 54.8? Great. And do we have a standard deviation? Not quite. Let's see. I will try to do this quickly. 5.8 squared plus 0.2 squared plus... Okay, my standard deviation is 4.15. Yes.
Is this the original standard deviation from chapter 2?
Yeah, this is the original standard deviation. We find this. Okay. Right, we remember this in chapter 3. Hmm?
No, I just asked what she said.
The sum? The summation sign? Yeah. Okay, so anyway, so I did this quickly and we got 4.15, I think. Well, anyway, it doesn't really matter for this. Alright, so now we're going to make a confidence interval, okay? And so we have X bar, and I have S, and my N is what? 5, right? Okay, so based on these 5 pizzas, I'm going to try to make a statement about all pizzas from Costco, okay? And make a statement about the population, alright? So I'm going to say, okay, well, what I observed was an average of 54.8 slices, pieces of pepperoni, okay? And we've got to create a margin of error, okay? And so the margin of error is going to be T star times our standard error, and my standard error is S over the square root of N. So my S is 4.15, and my square root of N is going to be the square root of 5. Alright, so this is where we're going to use our table to figure out our T star. Okay, so for a 95% confidence interval, I'm going to go to my table, and I'm going to go to the column that says confidence level 95%. Okay? And that's right above the thing that says T.025. Okay, so in your table you see 95%, and it's right over T.025. You see that? Okay. Why do you think this says T.025?
C equals 0.025. T star equals.
Yeah, so what happens is, if I'm going for the middle 95% in a distribution, how much is going to be left over in each tail? So I have a total of 5% left over, right? Because I've got 95% in the middle, so a total of 5% left over, but it's going to be split between two things. So 5% divided by 2 gives me 2.5%, which is 0.025. Okay, and you'll see that relationship holds up for all the other numbers, okay? So if I create a 90% confidence interval, how much will be in each tail? 5%, right? And if you look at your table and you go to 90%, you see T.05. Okay? Alright, so here, that's the column I'm going to go to. The row that I use is I've got to figure out something called degrees of freedom. Okay? Degrees of freedom is equal to n minus 1 when we're dealing with one sample. Okay? So my degrees of freedom is equal to n minus 1. So I'm going to have 4 degrees of freedom. So what is the T that I'm going to use here? 2.776. Do we see that? Yes, question.
Why do you have 95% why would you have 95%?
Because I decided to make a 95% confidence interval.
Oh,
Okay, I've chosen that. So you could make a different level confidence interval, but 95% is probably the most common. 90% is also common. 99 is also common. Yes.
How do we get to
2.776. Do you have one of these tables?
Yeah.
Okay, so you're in the column for T.025 or 95%, and then we're going to the row with 4 degrees of freedom. Why 4? Because my degrees of freedom is n minus 1.
Oh, 5 minus 1.
N minus 1.
And minus 1.
Okay, so I have
So it's like
54.8 plus or minus 2.776 times 4.15 over the square root of 5.
Oh,
right?
yeah.
And where's my calculator? So let's figure this out. Okay, so check, if you have your calculator, see if you could do this, and let's just make sure we know how to use our calculator properly, because that's a common problem. Sorry?
So, how'd you get that?
How did I get what? Okay. Wait, how did I get where? What?
'Cause you-
49.65.
Okay. There. Did we get, okay, have we done this part? Have we found the margin of error?
I don't know how to track it.
Yeah.
Plus or minus is kind of throwing me off.
The plus or minus, is that throwing us off?
Well, like, if you just do plus first and then minus.
Okay, plus or
Oh,
minus,
yeah.
yeah, plus first and then the minus. But can we get 5.15? Yes or no?
Yes.
No?
No, I lost you after the 2.776.
Okay. Alright. Figure this number out on your calculator. Okay, this part. This is my margin of error, right? We know that this is called the margin of error. So what is my margin of error?
One
5.15? Is that what we got? Because that's what I got.
I got 5.1.
Okay, so the margin of error, it looks like we put our estimate. This is the estimate based on our sample of 5 pizzas, right? The average from our 5 pizzas was 54.8 pieces of pepperoni. Okay, and so now I'm going to say, okay, well, I'm confident that the average number of pieces on any Costco pizza is going to be 54.8 plus or minus some margin of error. And that margin of error is 5.15. So on the high end, okay, or the upper end, I have 54.8 plus 5.15, which gives me what? 59.95. And then on the low end, I have 54.8 minus 5.15, which is going to give me 49.65. Okay? And so that's what this plus or minus means. Okay? Plus or minus means two things, plus and minus. Okay? Plus, minus. Yes, Nick?
Would it be a huge issue if it was like 5.14?
No, that's insignificant. I mean, so on the test, if it's multiple choice, okay, you came up with 5.14, and the options on the test were 5.15, you would pick 5.15, right? Okay, because I'm not going to list off one option being 5.15 and one option being 5.14. That's just me. Okay. Yes. Okay. Sometimes I'll give you S, but if you had to find S, you can do that, right?
Yeah.
How long did it? Okay.
Because I don't do the formula. I do it step by step. So
Yeah. I mean, I did it step by step also. Okay.
No, but it's
All right. Well, we'll see how generous I'm feeling. All right. Did we get this?
Yeah.
Yes. All right. All right. So here's my 95% confidence interval. And what is the interpretation?
I'm 95% confident.
I'm 95% confident. Great. That.
That the population proportion is between 49.65 and 59.95.
Okay. So I'll write this up. I think I heard something that's pretty good. But we'll just make sure we have our interpretation correct. I am 95% confident that, so our confidence interval is always about the population, okay? It's not about individual pizzas, it's not about future pizzas, it's about the population mean mu. So I'm 95% confident that mu, which is the mean number of pepperoni pizzas, alright? Or that the average number, if I know some of our brains still haven't quite embraced the word mean, so that the average number of pepperoni pieces is between 49.65 and 59.95 pieces. Okay. So if I order a single pizza, could I get 65 pieces of pepperoni?
You could.
I could, okay? Because this is not a statement about any individual pizza, alright? If I take a sample of 10 pizzas and I count up the number of pepperoni pieces and I get the average, could I get an average of 62?
Possible.
Yeah, I could, okay? Because this is not about a sample either. It's about the population. And it's saying if I went and I found all pizzas ever from Costco, ever, or whatever brand we're talking about, okay? Because I have a feeling Costco puts way more pieces of pepperoni on this, alright, just from my experience here. And we found the average of all the pieces of pizza, pieces of pepperoni on all the pizzas that they've ever made. We're 95% confident that that average number is between 49.65 and 59.95. Okay? So it's a confidence interval about mu. Alright. Based on this, do we have evidence that mu, the mean or average number of pepperoni pieces, is not 62 pieces?
No.
I would say we do have evidence, okay? I mean, it's possible that the average number of pepperoni pieces is 62, but that would be surprising to us, okay? Because according to our data, we're 95% confident that the average number is between 49 something and 59 something, okay? We're confident that the average number is within this range, so we would say we have evidence, okay? We have evidence that mu is not 62, or any number outside of the interval. And we understand the idea of being outside of the interval, right? Yes?
What is the difference between the margin of error and S?
S is the standard deviation coming from my sample. Okay.
The margin of error.
The
is
margin of
from-
error is my t times the standard error.
If we have a standard deviation, why did we use that as the margin of error?
Okay, so my standard deviation is 4.15. My margin of error after I did the math turned out to be 5.15.
Okay.
Okay, so we're not going plus or minus one standard deviation. We're going plus or minus my margin of error, which sometimes is smaller than the standard deviation, sometimes it's bigger than the standard deviation, depending on the situation. If we have a large sample, it's generally going to be smaller than the standard deviation. If we have a small sample, it will generally be larger. So depending on our data, it depends. Okay, so we have evidence that mu is not 62. Okay, we have evidence that mu is not 60. Yes, because 60 is outside of my interval. Okay, barely, but it's still outside of my interval. Okay. On the other hand, do we have evidence that mu is not 55? No, because 55
It's within.
is inside the interval. Okay. So on the other hand, we do not have evidence that mu is not 55 or any other number inside the interval. And this line of reasoning applied when we made confidence intervals for proportions, right? Yes. Okay, is that all right? Yes, question.
Will we have to write those type of statements in our homework?
I think it's a good habit to. Okay. You know, with the homeworks, I don't check very thoroughly, and some of you guys have taken advantage of that, but I'm not gonna. I won't judge your character, but maybe a little bit. All right, so that was a confidence interval. We've observed a sample, and based on the sample, we're making a statement about the population. And in this case, we observed a sample mean, and based on our sample mean, we're making a statement about the population mean, or the population average. Okay. And last chapter, what did we do? We didn't do confidence intervals, we made hypothesis tests, right? Okay, so this is a hypothesis test for a numeric variable. Based on one sample. Okay. Or sometimes we'll call this one sample mean, because it's a hypothesis test about the mean. One sample mean hypothesis test. How does a hypothesis test work? Yeah, we create a null and an alternative hypothesis, right? And what does the null hypothesis usually state?
Our hypothesis that remains the same as the proof.
Okay, so the null hypothesis, yeah, sometimes we'll call it the status quo. Last chapter was that the population proportion had a certain value, okay? And then the alternative would be that the population proportion did not have that value.
Yeah.
That was for one sample proportion, right? Okay, but here we're not dealing with proportions. So what do you think our null hypothesis is going to state? That the mean is some value here, okay? So our null hypothesis is that mu, which is the mean of what? The mean of the population is equal to some number, okay? So just for illustration, I'm going to say that the mean is equal to 7. Right. And then the alternative would then be that the mean does not equal 70. Or we could also have that the mean is less than 70 or that the mean is bigger than 70, right? Also, we can have depending on the question. So that's our null and our alternative hypothesis. All right, and then so we find a p-value. Okay. Can anyone tell me what a p-value is? It's a probability
of observing our data.
Like the sample.
It's the probability of, observing your data or of getting your sample, or something more extreme,
If we assume that the null hypothesis were true.
if we assume that the null hypothesis were true. Okay? Okay, so what might have an average of 70? Maybe this is, what's the average weight of, what weighs around 70 pounds? A big dog, okay? So a German Shepherd, okay? So maybe we say, is the average weight of a German Shepherd 70 pounds or not? Okay, so we say this is the question. Is the average weight of a German Shepherd 70 pounds? Okay. Well, that's maybe one of the questions we're sitting out to go. So we gather data, okay? Gather data. All right, so let's just make up some numbers together. Okay, how many? So to do this, we gather a random sample of German Shepherds somehow. Okay, and so how many dogs did we look at? 10 dogs? Huh? Okay, well, let's just say, okay, so we looked at 10 dogs, okay? And then, and what was the average weight of the 10 dogs that we looked at? So I could list off all 10 numbers, but just for shortcuts, we'll just go ahead and jump straight to the average and the standard deviation. So what was the average of these?
110.
Huh? 100 pounds?
No, these guys are big.
Huh?
65.
Okay, yeah, okay. So let's say that the average weight of these 10 dogs was 65 pounds. Okay, is that all right?
Yes.
No? We need bigger dogs? I don't know. Let's just say 65 pounds. Sorry if that's unsatisfying. Okay, maybe you know more about German Shepherds than me, which you probably do. They're good dogs. Okay. And okay, and then let's say the standard deviation was 6 pounds. Okay. So from our sample, there was a standard deviation of 6 pounds. So some dogs weighed more, some dogs weighed less, and the overall spread between these 10 dogs were 6 pounds. Okay, so here's the question. My sample, the average weight of my sample was 65 pounds, okay? And somebody's asking, is the average weight 70 pounds? So based on our sample, is this evidence that the German Shepherd's average weight is not 70 pounds?
No.
Okay, well,
Yeah, it is.
all right, so we'll say, is this evidence that the average weight of a German Shepherd dog is not 70 pounds? Okay, so we understand the question here? All right, and someone said no. Who said no? Okay, why do you say no?
Because the give or take is gonna be close to 6 pounds.
Okay, all right. So the truth is we got to do some more math. But you're saying that here, if the true weight is 70 pounds, whenever I take a random sample of dogs, maybe I get an average of 65 pounds. All right, and that's what we need to check. We say, so the p-value is what's the probability of observing our data or something more extreme if the null hypothesis were true. So if the null hypothesis were true, anytime I take a sample of 10 dogs or 10 German Shepherds, what would I expect my average to be?
70 pounds.
I would expect my average to be 70 pounds if this statement were actually true. Okay? Now, of course, because of random chance, I might not get exactly 70 pounds. And today I got an average of 65. So the question is the difference between what I expected, I'm expecting 70, and what I got, which was 65, is that difference a big deal or is it not a big deal?
5 pounds is a lot.
Could be.
Okay, so yeah,
Say yes.
5 pounds, is that a lot or is that not a lot? Okay. All right. So some of you guys get upset if your weight fluctuates 5 pounds, but maybe maybe it's not a big deal when it comes to the average weight of German Shepherds, okay?
I have a quick question.
Yeah.
When you say or something more extreme,
Mhm.
does that, like, what does that mean? Does that mean something heavy weighs 70 pounds?
No, okay, so if the true weight is 70 pounds, we are expecting our averages to be 70 pounds, okay? What we observed was 65 pounds, okay? And the question is, should this set off alarms about whether or not German Shepherds could actually be 70 pounds or not? Okay, so if 65 pounds set off the alarm, then anything more extreme than that should also set off the alarm, right? So 65 pounds is 5 pounds less than 70. So if we get something that's 6 pounds less, meaning we get 64 pounds, or 10 pounds less, meaning we get 60 pounds, okay? So basically 65 pounds or lower should set off the alarms.
Observing that or something even further away
Yeah,
from the
something
mean.
even further away from the mean. So 65 pounds is 5 pounds away from the mean going down. Also equally extreme in the opposite direction would be if we got an average of what?
75.
75 or higher. Okay, so that's what this idea of something more extreme. Okay.
So 70 is extreme or it's not extreme?
Well, that's what we're trying to find out. Okay. So 70, we're expecting 70. If the null hypothesis were true, we're expecting 70, and we observed 65. So is 65 really unusual, or is it possible that this results from just random chance? Okay. So we're going to ask, what is the probability of observing our data or something more extreme okay, and that means in this case getting in a sample average that's more than 5 pounds away from the mean, okay? Getting an X bar that is 5 or more pounds away from 7. Okay, so what's the probability of observing our data or something more extreme if the null hypothesis were true? I know I'm repeating myself and saying a lot of the same things over and over again. I do this in the hope that one day all of this information will click. Okay? And one day being before the final exam. You know, I know we hate memorizing stuff, but there is some merit to memorizing things. And I think memorizing the definition of a p-value is a good thing. And if you say it over and over again, I think eventually it will click, right? I don't know. Did you guys ever have to recite the Pledge of Allegiance in elementary school? Okay, some of you did, okay? Did you guys ever have a moment where the Pledge of Allegiance was no longer just, because when you first learned it in like first grade, it was probably just like a bunch of big words that you didn't fully understand. But then one day, after saying the Pledge of Allegiance so many times, you finally understood what the sentence was saying? Did that ever happen to you guys or not? No? Who could say the Pledge of Allegiance? What? Alright. Somebody, just shout it out here. I pledge of allegiance, come on. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, with liberty and justice for all, right?
No, you said wrong.
Huh? Oh, wait. One nation under God, indivisible, with liberty and justice for all. Yeah. Okay? And then so, well, maybe you guys didn't have this experience, okay? But, you know, there's a time where after you say it so many times, one day you sit back and you think of the words that the thing actually says, and you're like, oh, that's what the Pledge of Allegiance means. Or maybe you never experienced that. That's okay. Well, I'm hoping if you try it out with the p-value, alright, in the beginning it just feels like this gibberish statement, right? So it's the probability of observing your data or something more extreme if we assume that the null hypothesis were true. Okay? But maybe after you say it a bunch of times, one day the definition will click and you'll understand what it's actually saying. And I hope that happens relatively soon for you guys. Well, anyway.
Professor,
Yes.
I have a question.
Okay.
Does that mean basically, what are the chances of getting 70 plus or minus 5?
Not 70 plus or minus 5, okay? Because here we're assuming
Oh.
that the null hypothesis were true, okay? We're assuming that the average weight of German Shepherd dogs is actually 70 pounds, okay? So if that were actually true, then when I take a random sample of 10 dogs and I get an average of 65, that's an anomaly, right? That's different from what I expected. And the question is the fact that the average is 65, is that within the realm of what could normally happen, or is that something that we would regard as highly unusual? Okay? Yeah, Philip.
How does the central limit theorem apply to this?
Yeah,
Do we have to test for anything before we even go further?
we should, okay? We should, and I'll get to that, okay? I'm going through the process now, and we'll get to that. And the fact that we're using the t distribution means we're using the central limit theorem. Okay. So, you know, for example, okay, if you go to the doctor, right? If you go to the doctor and then you got something on your skin, right? And you say, you know, doctor, should I be worried about this? Okay? And the doctor says, and he looks at it and he says, oh, no, it's just a mole, but it doesn't look like it's a problem. Okay? Because technically, no, you're not supposed to have moles on your skin, but sometimes moles grow and whatever. Sometimes it's a problem and sometimes it's not. And the doctor's supposed to make an evaluation. So sometimes a mole develops, and it's nothing unusual. It's just within the quote what might be normal or what might not be that unusual as a mole. Other times you go to a doctor and you show him whatever's growing on your skin, and he says it shouldn't be like that, right? He says, okay, we better get this checked out, and you know, just make sure that everything's fine. Okay, and what we're saying is, if we assumed you were healthy, if we assumed you were a healthy person, what's the probability that you would develop a mole that looks like this? If the probability is that it's pretty high, being a not unusual mole, then you'd say it's nothing to worry about. But if we assumed you were healthy, you know, what's the probability that you grow this, you know, 5-inch tumor on your arm? Probably pretty low, okay? And that's why we would say, oh, something's not quite right. So, if we assume that the average weight of a German Shepherd dog is 70 pounds, what's the probability that I would get a sample of size 10 where the average was 65 pounds? That's what we're asking, okay? So if mu is equal to 70 pounds, what is the probability that x bar is 65 or less, okay? And or more extreme, or 75 or more. Okay, this is what. If the null hypothesis were true, anytime I take a sample and I calculate the average, I'm expecting 70 pounds. What I observed was 65 pounds. And I want to know what's the probability of getting 65 or less. Okay? And more extreme would be going in the opposite direction and doing 75 or more. Okay? Do we know how to get these numbers? Yes, kind of, but actually no. All right? Because this looks like the normal distribution, but it's technically not. We're using the t distribution, so I got to teach you something new. Okay? But if we were looking for a z-score, we would do what? 65 minus 70 divided by the standard deviation. Okay? But here my standard deviation, for the standard deviation, use the standard error, which is equal to s over the square root of n. Okay? And it's technically not going to be a z-score, it's a t-score or test statistic. And this would be equal to the observation minus the mean, or what I expected, divided by my standard error. Okay? So in this case, I would do 65 minus 70 divided by my standard error. So what's my standard error? 6 over the square root of 10. Yeah. 1.897? Okay. All right, is everybody with me so far? Okay, so I'm going to get 1.897. So what is my test statistic? I do 65 minus 70 divided by 1.897, and I get, yeah, negative 2.635. Or something around there. Okay, I'm not done. All right. Now, so far I've gotten just my test statistic or my t-score, which is kind of like getting my z-score. Okay. I know when I was grading the quizzes, okay, I noticed a lot of you got your z-score and you stopped. Okay, for the problem about like the Lego blocks and stuff. You guys got a z-score, and some of you guys stopped. Okay. Don't stop there. You've got to look it up in a table. Usually, if you don't use a table, you're probably doing something wrong, okay? Because a lot of these require the use of a table. So just say, did I use the table? And if you didn't, you probably forgot a step, okay?
Wait, where did you use the table?
Huh?
For what?
I haven't used the table yet. We're going to use the table
okay.
now, okay? I'm saying we're not done. Your answer is not 2.635. We got to look this up in a table. All right. So when I go to my table, how many degrees of freedom do I have? 9, right? Degrees of freedom is n minus 1. So I'm going to go to 9 degrees of freedom.
Are most problems going to be 95% confidence, or does it just depend on the situation?
So here there's no confidence level because we're not making a confidence interval. We're doing a hypothesis test, so there's no confidence level. Okay. We do have a significance level, which is the alpha, where we decide to reject or not reject, which in most cases is 5%. Okay. So we've got 9 degrees of freedom. Okay. And so I'm going to list off the numbers that I see in 9 degrees of freedom. I got 1.383, 1.833, 2.262, 2.821, and 3.250. Alright? And this corresponds to T.1, T.05, T.025, and 0.010, right? Am I writing this?
Yeah.
And T.005. Okay. All right. Are we able? Did I do an okay job of copying the table onto the board?
Yeah.
Okay. Okay. So our test statistic is negative 2.635. Negative 2.635. So what we want to know is how much is in this tail and how much is in that tail. Okay? So let me tell you how we use this table, okay? So this is what the t-distribution looks like. It says if my t-score is 0 and I shade everything to the right, I would have 50%, okay? It says if I draw a line at 1.383, the amount that I would have in the tail is 0.1000. Does that make sense? And it says if I drew a line at 1.833, how much would I have in the tail? 5%, okay? And that makes sense, right? My number is getting bigger, right? Because I'm getting further away from the mean. So the amount that's going to be left in this piece gets smaller and smaller, okay? So some people get confused because these numbers are getting bigger, but the numbers across the top get smaller. It's because I'm getting further and further away from the mean. So the amount that's left over gets smaller and smaller. Okay, so the question is, if I drew a line at 2.635, let's just ignore the minus sign for now. The question is, if I draw a line at 2.635, how much is in my tail? Okay. So the answer is, we don't know exactly, okay? But I do know that if I drew a line at 2.262, I would have 0.025 in the tail. And if I drew a line at 2.821, I would have 0.01 in the tail, right? So if I drew a line over here at 2.262, I would have 0.025. And if I drew the line at at 2.821, I would have 0.01 in the tail. So the amount, if I drew it at 2.635, 2.635 fits in between here and here. So the amount that I would have in the tail, I don't know exactly how much, but I do know it's going to be more than 1%, but less than 2.5%. Okay? So my tail area is more than 1%, but less than 2.5%. Yes?
So without the confidence interval,
There-
how do you know what two numbers to pick?
There's no confidence interval here, okay? We're doing a hypothesis test. So I'm just asking how much is in the tail, okay? How much is in the tail when my test statistic is 2.635? The amount that's in the tail, I don't know exactly how much, but I do know it's less than 2.5%, but more than 1%. Okay? And I know I said we ignore the minus sign here, okay? Because the table always gives us only positive values. But because it's symmetric, the tail over here is also going to be more than 1%, but less than 2.5%. Okay? So the total tail area is going to be between what and what? I would have to add the two tails together, and I would say the total tail area, I don't know exactly what it is, but it's going to be more than 2%, but less than 5%. Because I'm adding 0.01 and 0.01 and 0.025 and 025. I'm adding.
Wait, before you had it up there, 0.025, and then 0.01, and now it's changed? Sorry, I was writing
Yeah.
it
Okay.
down. I was-
So I have this tail is between 1% and 2.5%, right? And this tail is also between 1% and 2.5%. So
Why is it opposite? Then why what we have written up there?
Oh, that doesn't matter, right?
Doesn't matter? Okay.
It doesn't matter, okay? So to say 1% less than the tail, less than 2.5%, that's saying the same thing as 2.5% is more than the tail, which is more than 1%. All right, is that confusing?
No.
Okay. All right. We got to get used to our. I don't know. This is like just inequalities. All right. So I'm sorry. You know that the signs of the I don't know. The direction of the inequalities are reversed, but it's saying the same thing. Okay. Because the what you learned it as the alligator preferring the larger
Cookie
thing.
Monster.
Whatever. The Pac-Man. Okay. Wants the bigger number, okay, it's still pointing in the same direction, okay? So the inequality still points in the same direction, so we're still fine, okay? And we're just saying that if I took, this tail is between 1 and 2.5%, and this tail is between 1 and 2.5%, and I add those two together, my total tail is going to be between 2% and 5%, because I'm adding those numbers up.
Wait, you're adding what number?
I'm adding 1% and 1% to get 2%, and 2.5% and 2.5% to get 5%.
Okay.
So my total tail area is between 2% and 5%. Okay? And what do we call this thing? This is the answer to the question, what is the probability of observing our data or something more extreme if the null hypothesis were true? This thing has a name. What's that called? The p-value, okay? So my p-value, whatever it is, I don't have an exact number, is less than 5%, but more than 2%. Is that okay? What if I chose a significance level, alpha equal to 0.05? What do I do? We learned this, right? Significance level, so if my significance level is 5%, is my p-value bigger than my significance level or smaller?
Smaller? Or it's more?
It's smaller, right? I don't know exactly what it is, but I do know for sure that my p-value is less than 5%. Okay? So even though I don't know what it is, I do know my p-value is less than alpha. So in that case, what do I do? My p-value is less than alpha, so that means we reject the null hypothesis. We reject the null hypothesis. Now what was my null hypothesis? That the average weight of a German Shepherd dog is 70 pounds. And so I reject that, and now I say I have evidence that the average weight of a German Shepherd dog is not 70 pounds, but something a little less than that. Or something less than that. Right? Because if my p-value says that if the average weight of a German Shepherd dog were actually 70 pounds, the probability that I take 10 random dogs and get an average of only 65 pounds, that probability is less than 5%. Okay, and because it's less than 5%, I'm willing to rule out the possibility that it happened by chance. And I would say the fact that my average was 65 is actually a big deal if I'm expecting the average to be 70. Okay, so you know this difference of 5 pounds, it doesn't seem like much, but it's actually a big deal in this case, in this scenario. Okay, other scenarios maybe not, because you might have different data. Yes.
The thing that catches me off guard is I didn't think it seemed like a big deal because the standard deviation was 6 pounds, so that's 65 is within one standard deviation.
Yeah, it is, you're right. But the fact that I took 10 dogs, okay, ends up shrinking my standard error, okay? So we can't, we can no longer just say, is it within one standard deviation of the mean or something like that, okay? We now have to think in standard errors, which take into account how much data I collected, okay? If I only collected one dog, then we can't say much. But if I've taken data on 10 dogs, then this actually makes a stronger statement, okay? Yeah?
You know how it's between 2% and 5%? it's not true, that it had to be above 50% for it to be true?
No, it's,
How do you figure out if it's true or not? Like, if
okay,
you
so
reject or
the
not?
statement isn't, we shouldn't say true or not true. The
Reject.
statement is we reject
Yeah.
the null or we don't reject the null, okay? And anytime our p-value is less than alpha, and alpha in this case was 5%, we reject the null. Okay, so if our p-value is less than alpha, we reject the null. And so in our case, we got a p-value that's less than 5%.